Keep full screen in both places.
Yeah, I wanted, but
okay. So let me do it.
Oh, maybe it have it. Okay. So can you also get rid of?
Oh, this is now being mirrored. So I'm gonna put it. I'm gonna put it somewhere here.
Okay. And this one.
Let's hide this one.
Okay, perfect. Thank you. Good? Yeah, perfect. Thank you.
Did you unmute your microphone?
Yes. Maybe you can check in Zoom. Okay. Good afternoon, everyone. Is my voice audible in Zoom? And perfect. Okay, let's get it started. So good afternoon, everyone. So we had actually less attendees last Friday, I think, because it was a breach day. So I'm going to introduce myself a bit, again. So I'm Mohammad. I'm one of the instructors in this course. So from last week, I started to basically take over some lectures about advanced topics in computer architecture. So we covered the out-of-order execution last week. And today we're going to continue with another fascinating topic, SIMD and GPU architecture. SIMD is abbreviated by single instruction, multiple data. So we're going to learn a lot. So the whole thing is about how we can provide better parallelism and enjoy the natural parallelism that we might have in our applications. So this lecture is going to be the last lecture that we cover about processing and how we can make things faster in terms of computation. Starting from tomorrow, we're going to jump into details about memory. So we're going to have a lecture on memory organization, memory technology, and we will continue that through basically cache hierarchy, as well as some other advanced topics like virtual memory and cache data prefetching. Okay, so I'm not going to bore you more about this introduction, and we can start the lecture. So, for this lecture, this one is some readings that you might want to check. So the first one is about one of the NVIDIA architecture. This is like IEEE micro paper, which so the level of details in that paper is more or less, is understandable, easy, even for people that they are not, experienced with computer architecture. So I would really suggest everyone to check this beautiful paper. And the second one is also recommended, which is like the extension for the instruction set architecture for Intel systems, such that they could provide SIMD instructions. So we're going to learn about SIMD and also how we can benefit from that, but and also the modern architectures that they provide that extension. So basically, we want to exploit data parallelism, and we're going to see what is data parallelism. And SIMD architectures and GPUs are prime examples of the architectures that they are benefiting from data parallelism. So SIMD processing, which is like another version of that, we can call it as exploiting, the system that's going to exploit regular parallelism, and it can be regular data parallelism as well. We're going to see that later in this lecture that GPU actually makes it a little bit easier. Then they can also provide good performance even for irregular parallelism. But SIMD architectures, they are really basically focused on providing SIMD acceleration. They are more or less useful for regular parallelism. So before going through that, I like to provide this kind of background from Flynn's taxonomy of computers. This is actually a paper from Mike Flynn. You can see it's around like 60 years ago. That basically Flynn categorized computers depending on how many instructions do what to how many pieces of data, basically. So the simplest architecture that we have been actually covering that is SIST. That is essentially single instruction operates on single data elements, which is really similar to the architectures that we have been discussed in this course so far. Another version is SIMD. That's basically single instruction operates on multiple data elements. When you have imagine that you have big vector and you want to basically add the two vectors like the element wise. So you can actually, your instruction is very simple, is one single addition instruction, and you want to run it on a multiple or thousands of data elements. So this kind of architecture are called as SIMD. That prime examples of them are array processor and vector processor that we're gonna discuss briefly today. Another version is MIST, which is multiple instructions operate on single data element. This might sound a bit weird, but essentially what mean here is that we have single element of data, and it actually goes through different instructions. So there is an instruction or processing element that takes that input, that data as an input, operate on it and provide an output. And that output goes to another processing element and so on and so forth. So this kind of architecture calls basic MIST. And so the closest form of MIST is actually systolic array processor. We haven't covered systolic array processor in this course this semester. But I'm going to flash some slides about systolic array that you can watch those lectures from past if you're interested. But essentially, systolic array is a fascinating topic also because many of today's accelerators, especially for machine learning, they are based on systolic array. So like Google TPU that you may have heard about it is actually essentially the systolic processor, systolic array processor. And the last item, which I would say most of the computer these days are using, that is MIMD, that multiple instructions operate on multiple data elements. And it can be multi-processors or multi-threaded processor that you have you have all used them in your computers, laptops, smartphones, essentially everywhere. Okay, so this is the paper from Flynn that you may want to review it, optional. The title is Very High-Speed Computing Systems. So this is the example of MIST, multiple instruction, single data, that, as I said, essentially you have a data storage that you bring data, you load data from storage, and you basically fetch it to the execution unit, and then fetch to another execution unit, and pass it to another execution unit, and so on and so forth. So this kind of architecture is called as MIST, the way that Flynn was envisioning at that moment. And it's actually very similar to systolic array, like a generalized form of systolic array. As I said, we haven't discussed systolic array in detail in this course. But if you are interested, you can actually watch this lecture from past about systolic array. I think you're gonna like this lecture because it's a fascinating topic that have a lot of impact on today's accelerators for machine learning. And this one is a SIMD architecture from Flynn. So the way that basically Flynn was envisioning was that, so we have basically some operand storage that, here, And essentially, you have a instruction storage. So you fetch one instruction, and you have one instruction, but this instruction is going to fit to many, many operands at the same time. So this kind of architecture is like single instruction is going to operate on multiple data. And that multiple can be actually quite, I mean, as I said, a lot of data elements can be like millions of data elements. So we're going to learn about this SIMD architecture in more detail. Okay. So let me give you some background about data parallelism. So basically, concurrency arises from performing the same operation on different pieces of data. This is the meaning of data parallelism. And the prime example of the system that they try to benefit from such parallelism is single instruction, multiple data. So you can actually think of many examples here, like dot product of two vectors, or for example, when you want to add, as I said, two vectors. So basically, your instruction is just simple addition, but you want to operate that instruction on many operands in parallel. So you have a lot of data parallelism. And the good thing about that is that basically your parallelism is quite regular, and you don't need to basically make a lot of arrangements between your processing elements. So all these addition instructions that they are operating in parallel, they don't really need to communicate stuff to each other, because that communication, you're going to see later that, cause some performance, limitation that in parallel architecture, we always have that problem. But when you actually can benefit from SIMD and pure data parallelism, your life is quite nice. So I like to contrast it a bit with other type of parallelism that we have seen so far, like data flow. This one was the parallelism that we discussed in detail last week about out-of-order processing, that we say that basically, even though the von Neumann model, dictates that we need to operate on instructions like in a sequential manner, but internally, in microarchitecture, you can actually run your instructions out of order. And as long as you commit your instructions in order, like in the right order, in the order that programmer mentioned, you're going to be safe. So that was the topic of the last lecture. And we discussed about creating that kind of data flow graph internally by using basically all these controller and data structures that we discussed, like the reservation station and basically reorder buffer. So, but yeah, basically data parallelism is different from that. And also we have like to contrast it with thread parallelism. So basically here, so with thread parallelism, concurrency arises from executing different threads of control in parallel. So you have application, and this application can have many threads, and those threads might not actually do the same thing, but you're actually benefiting from multi-threaded execution. How many of you have taken parallel architecture or parallel programming course? So you guys should actually, I think you are familiar with the whole concept, right? That we have multi-threaded, and which language you use to write parallel? Java, okay. And in Java, you can create threads as well, right? Yeah. Okay, nice. So I can actually go faster. So SIMD exploits operation level parallelism on different data. This is single instruction, multiple data. And basically, as I said, the same operation concurrently applied to different pieces of data. And this one is actually very similar to instruction level parallelism that we have discussed a lot. So you have learned about instruction level parallelism actually in pipeline lecture, for example, when we wanted to accelerate the execution using pipeline processor. And we even, went step even further about using out-of-order execution in order to maximize, our capture of ILP. But essentially, when you have kind of data parallelism, so you're gonna have one, let's say, instruction like addition on many elements of data. And so you can, using SIMD kind of architecture, you can actually just define only one instruction, which is addition, and then ask the system to run it on multiple data elements. But if you also think about traditional architecture, I mean, the architecture that we have discussed so far, like this SISD, so essentially what's going to happen is that you're going to have millions of additions, right? So you're going to have millions of additions that they're going to, basically each addition is going to operate on different data elements, right? And since all these additions are independent, right? Because the data that you are working on is, the operands are completely different. So essentially you're going to have instruction level parallelism. So that's why we, when we think about SIMD, we should also consider this is also not really different from instruction level parallelism. So there are many instructions that they are basically independent, and you can run them in parallel. So this SIMD processing paradigm is, like single instruction operates on multiple data elements, and it can be in time or space, or in space, like the duality. So we have seen this one actually also before a bit, like the parallelism in time is actually can consider like the pipeline processor, right? So you have so using pipeline processor that Frank actually taught it nicely. We actually have kind of parallelism in time. So whenever you at the single cycle, when you check your system, you're going to see that you are operating on different things, right? So one instruction is the decode stage, another one is the fetch, the other one the execution, the other one is the write back. So there are different steps of your basically computation, and the instructions are running through them. But your parallelism can be also in a space, which means that you're going to have multiple elements of similar thing, like multiple addition unit, multiple multiplication unit, or multiple fetch unit, multiple decode units, and you're going to use them in parallel, which is essentially what we are using in GPUs, for example, or in multi-core systems. So we're going to see more about these parallelism in time or in space in this course, in this lecture. So yeah, essentially we have, as I said, multiple processing elements, and we have this time-space duality. So now actually the definition of array processor and vector processor can be clarified. So in array processor is the processor that benefits from SIMD architecture, but essentially the implementation is that instructions operate on multiple data elements at the same time using different spaces. So in array processor, you have multiple copies of the same processing element. So the parallelism is in space. And you can actually, benefit from SIMD. So array processors are quite fast, and they provide very good parallelism, but they are costly because you need to copy many processing elements. And that processing element essentially should provide all the operations that you need. I mean, each of them should be able to basically do addition, multiplication, load, store. I mean, any operations that you can think of. So that's array processor. And because of the cost, actually, we have vector processor as well, which is basically the difference that you have basic instruction operands on multiple data elements in consecutive time steps using the same space. So you can actually have only one processing element, and you run your instructions in basically in the consecutive time steps using that. It's very similar to what we have seen so far in pipeline processor, basically. So yeah, I mean, vector processors were quite famous and useful in the past because we were really limited by the resource, by the number of transistors that we can integrate in our chips. But today, actually, because we are not that limited, array processors are also quite famous, and today's systems are actually the mixture of vector processor and array processor. We're going to see a prime example of that, which is GPU. That GPU are essentially array and vector processor, and that they combine these two paradigms. So before providing you an example of array and vector processor, I'd like to also mention one more thing about this architecture. This is actually important for every SIMD architecture, that we need vector data registers. So far you learned about register file, that we have like registers in SISD architecture that They can be 32-bit, for example, in MIPS architecture, but they can be also bigger, like 64, 128, 256 bits, and so on. But here for vector processor and for array processor, we need the vector data register. So you're basically your register in the hardware, they should be able to store vectors. And so vector is, I mean, I think you know what is vector, right? It's an array of elements. So you have multiple elements. And when you load this array to your system, you should be able to load it to different register elements, basically. So your register file, actually your register is going to be much bigger. And yeah, and that's the definition of vector data register. So each register would store a vector and not a single scalar value as we saw before, as we discussed. So here is an example that you have vector register 0 and vector register 1 and so on. And basically you input these two vector registers to your processing elements, essentially. Any question so far? Okay. So now let's see, basically learn more about array and vector processor. This is a very simple assembly code that I have here for this SIMD architecture. So we have 4 instructions. The first one is, but those are like vector instructions. The first instruction is load, which means, so we want to load a vector of A, the 4 elements of that vector, to a vector register. So basically this instruction load array A 3 to 0 to vector register. And then we want to add the vector register by 1, which means that we want to add each element by 1. And then we want to multiply each element by 2. So you're going to see that we have some dependency here that, so we need to be done by the addition such that we can go to multiplication, because these are dependent on each other. We have read after write dependency here. And after all, we have this store that you store your vector register to the same array space. Okay, makes sense? This is the instruction that we have, the simple code. So now we have 2 kind of SIMD processor here, the array processor and vector processor. In array processor, we consider that we have 4 processing elements. And essentially, each of these processing elements is able to do everything, right? So in the first cycle, and this vertical line is also the time. So in the first cycle, you basically do load 0, load 1, load 2, load 3, which means that you're doing the load operation for all these array elements in parallel, because you have 4 processing elements. And after that, you need to do addition by 1. And then you do multiplication, and then you do store, right? So this is simple, this array processor. However, in vector processor, we assume that we have only 1 processing element. And in that processing element, you have different functional units. So you have a function for load, you have function for addition, multiplication, and store. And essentially, you need to pipeline it. So you do only at the first cycle, you can do the load only for the first element of your vector, but then you need to go to the second cycle. So in the second cycle, you do the load for the second element, and you do the addition for the first element that you have already fetched, you have already read from memory, and so on and so forth. Basically, you do the load of the third operand, and then addition of the second, and also the multiplication of the first. And you basically continue this pipeline execution until you're done. So you can see that the vector processor can take some longer time, but this is also, I would like to also mention that if your vector is large enough, long enough, basically you have a lot of elements, at some point, basically your pipeline is going to be full, and you're going to reach to that steady state, which means that at every single cycle, you are doing 4 operations at the same time. So in the end, you're going to have good performance. So because in array processor, at every cycle, we are doing 4 operations, right? But in vector processor, you can see that in the first cycle or in the cycle 0, we only do 1 operation. In the cycle 1, we do 2 operations. then 3, and then 4, and then because our basically code is so simple, then the pipeline is getting empty. So that's the thing. If you have this line that you have 4 instructions, more and more, you're going to have actually good throughput from that vector processor as well. So in the end, the performance is comparable to array processor. So you can see that in array processor, we are doing the same operation at the same time. And but in vector processor, we are doing different operations at time. And the x-axis, if you consider as a space, in array processor, you are doing different operations at the same space at the price of higher cost. But in vector processor, you are doing same operation at every space. And that's why vector processor were quite interesting in the past, that we were quite constrained by the hardware cost. Make sense, no? Okay. Any questions? Perfect. So we haven't also discussed VLIW in this course, but I briefly mentioned it last week when I was talking about out-of-order execution. I mentioned that basically in out-of-order execution, the goal is that we schedule instructions dynamically. So the hardware the hardware is tasked to find the parallelism, the instruction level parallelism from your instructions, and schedule them dynamically such that they can benefit from performance, the high parallelism. But there is also another way of doing that, which use compiler. So compiler can also try to capture and understand what are the independent instructions, and essentially pack them to one big or large instruction. So these VLIW basically architectures, they are using this is a very long instruction that it does addition, load, move, and multiplication. So this is VLIW. But in SIMD, the difference between SIMD array processing and VLIW is that in SIMD processing, we have only one instruction. So you don't really need to fetch, let's say, multiple instructions here. So here in VLIW, you need to fetch many instructions, and you need to decode them, understand them, and realize, okay, what to do. But the good thing about SIMD is that you fetch only one instruction, and then you can amortize the overhead of loading one instruction on multiple data elements, basically. So once you basically you load one instruction, after that you know that, okay, I know what I want to do, and then you're gonna repeat that your knowledge on many data elements, and that's why SIMD processors are quite useful. If you want to learn more about also VLIW architecture, I would recommend you to watch this optional lecture from past. Okay, so now let's get back to vector processor. So a vector is a one-dimensional array of numbers, and so you know that many actually scientific commercial programs, they use vectors. Like for example, in physics or all these area, there are many applications that they use big vectors. And in machine learning also, we are using matrix, and matrix are essentially also some vectors. So in the end, you can see that we see this vector in many applications. So yeah, a vector processor is one whose instructions operate on vectors rather than scalar values, as we discussed. But we need some basic requirements for such architecture. One is that we need to load and store vectors. So there should be some vector registers, as I discussed, to contain vectors. We should also know we should know how long basically our vector operation is going to be. So for that, we have this register, we call it vector length register, or VLEN, that essentially, so imagine that your vector register are, for example, long enough to store 50 data elements, for example. But at that moment, you don't have 50 data elements. So you want to do operation on 25 elements. So then actually you have this possibility to set this register vector length to 25, and that inform the architecture that your execution is going to be on 25 elements, for example. So And also we need to know how should we calculate the address of the next element. So for that, we have this vector stride register. And a stride essentially means that distance in memory between two elements of a vector. We're going to see an example about stride example. So for that, I'm using a matrix multiplication. So imagine that we have two A and B matrices that they both stored in memory in row major order, which means that elements that they are in the same row, they are actually storing in the consecutive address of the memory. So we have two, our matrices, matrix A and matrix B. And in memory, actually, so our memory architecture is a linear memory, right? So you need to store, even though your matrix is like two-dimensional or three-dimensional or anything, but you need to store them in one-dimensional in your in memory. So you can see that basically the elements that they are in the same row, they are actually coming consecutively when we store them in row major order. It can be also the other way around, column major order. And these things actually have a lot of impacts on basically locality, prefetching, all this stuff that we're gonna not jump into that topic today, but just basically have it in your mind. So we'd like to, so the operation that we want to do is basically multiplication of these two matrices. So the matrix A is 4 by 6 and B is 6 by 10. So in the end, your result is going to be 4 by 10. So what we need to do for every element of the output matrix is essentially doing the dot product of each row and of with each column vector of B. So for example, for C00, we need to actually do the dot product of this row, the row 0 of the matrix A, with the column 0 of the matrix B, right? So the thing is that we need to load these data to our vector registers. So we need to load first the first row of the matrix A to our vector register V1. So here actually, so each time we need to increment the address of the memory by 1. So when you want to load consecutive elements, you need to basically increment your address by 1 and you load it. So your stride is 1 basically, because everything is consecutive. But for matrix B, when you want to load the column into your vector register V2, for example, your stride is going to be 10 basically, because so after this address that you load, the second one, this one, you need to load it. And the offset of the address is 10. And then this one. So you need to set the stride to 10. And you can see that we might need to change the stride multiple times in a single code. So far, so good? Okay. So yeah, so vector processor, as we discussed, is like the vector instruction performs an operation on each element in consecutive cycles, and vector functional units are pipelines. We already covered that, and each pipeline stage operates on different data elements. So the good thing about vector instructions is that they allow deeper pipelines, and the main reason is that you really don't, so you don't have much, I mean, or at some point at all, dependency. You don't have data dependency because for between elements of your basically application, because all these operations are operating on different elements of data. So you don't really need to check the dependency across elements. And most of the time also we don't have much branches, because many of the branches that we have in normal basically implementation is because of the loops that we have. But you will see that with SIMD, actually we get rid of many loops. So you don't have a lot of branches. So basically your control hazard or control dependency is also getting reduced. So essentially you can design a pipeline at the low cost, because you don't need to deal with a lot of data dependency, control dependency, and those stuff that we have covered. So that allows you to have deeper pipelines and get benefit from that. And as I said, it's because of the no intra-vector dependencies, no control flow within a vector. And also we usually know a stride, right? So when we want to do the vector operation. And that allows us to, easily, calculate the address, the next address. And that can actually makes the whole life easier by basically enables easy loading or even early loading. So you can actually load even much before the moment that you need that, which we call it prefetching, that we're gonna cover on May 30, I guess. But yeah, basically, that's why we can use, deep pipeline for vector processors. So vector processors have several advantages. One is that, as I said, we have no dependencies within a vector. Each instruction generates a lot of work, as we also discussed. So you fetch one instruction, you decode, but then you operate that instruction on millions of data elements. I mean, in some cases, that might not be millions of data elements. It can be like few elements. And in those applications, actually, your benefit is going to be much less. But as long as your vector is long enough, you can actually amortize the fetch overhead and decode overhead on your computation. And that's why actually, SIMD processor, like array and vector processor, they usually provide high energy efficiency per operation, because you don't need to, do this fetch and decode all the time. And again, we don't need to explicitly code, loops, because so a big loop is going to be actually unrolled to vector instructions. We're going to see an example later. And that causes fewer branches in the instruction sequence, and less branches, meaning that means that you have less control dependency. And that causes much better performance. And and it provides a highly regular memory access pattern, which can be beneficial for some other optimization in your system, like using prefetching, your memory design. So yeah, but of course, every idea has also some disadvantages. So vector processor, they work only if parallelism is regular. So when our data parallelism is so natural, like, as I said, like vector addition, basically these vector processors are really good and they provide very good performance. But there are some applications that you have some source of parallelism, but your parallelism is not that regular. It can be irregular. For example, when you want to do some pointer chasing, like you have a linked list and you want to search for a key. And basically, essentially, you need to do a lot of pointer chasing. And for that, you're going to have a lot of irregular memory accesses. So unfortunately, vector processors and array processors, their performance is super basically bad for such kind of applications. And that's why basically, the paper from Fisher about VLIW actually mentioned this, that basically to program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. So that's a limitation that we have. And then, and Fisher tried to, basically overcomes this limitation by proposing VLIW. But later on, we also observed that VLIW also are not, they are good for some specific applications, but we cannot generalize it. Anyway, so we're going to also learn about GPUs, and GPUs actually make a nice, some decisions such that you can actually benefit also from irregular parallelism as well. So this is also a recommended paper for VLIW. If you are interested, you can read it. Okay, so parallelism is nice, and when we talk about parallelism, we always get quickly excited, but we should always pay attention to this Amdahl's law. So Amdahl's law is that Amdahl wrote this nice paper in 1967, which tried to model the speed up that you can get from parallelism. So the model is so simple, basically. So in every program, you have a parallelizable fraction of a program that we consider as f. For example, when f is 50%, which means that the half of your code can be parallelizable easily. Can be parallelizable, and the rest of your code is actually serial. and n is the number of processors that you can have. So our speed up is going to be something like that. So ideally, you should be able to reduce the amount, the time you spend on parallelizable portion by the factor of n. So if you have like 10 processor, ideally you should be able to reduce the time by 1/10. But unfortunately, the serial portion of your application, which is 1 minus f, cannot be accelerated. And that is a very sad basically phenomena. So if our parallelizable portion of the application is like 50%, imagine that you have basically infinite number of cores and infinite number of parallel processors. So this gonna lead to 0, right? F over n is gonna be like 0, but in the end your speed up is 1/1 minus 0.5, which is 2. So your speed up is gonna be at most 2, which is so sad, right? So we really want to work on our implementations, on our algorithm design, such that we can reduce the serial portion of the application as much as possible. And that serial portion might just be basically distributing the task to parallel threads, basically. So in every parallel code, you might have a master thread or something like that. The job for that is to distribute the task to multiple threads. So even though you want to have, you get rid of serial portion, but you might still have it. And this line of research is actually quite interesting still, that people try to come up with different algorithms, different implementation, such that they can benefit from parallelism as much as possible. So we really want to approach the parallelizable portion like 99.9999% of the application. And then, yeah, we can get 1,000, 10,000, or even more speed up by parallel programming. But because of this Amdahl law that we have this serial bottleneck, actually many processors that they basically try to benefit from SIMD, they also realize that they should also accelerate serial portion of the program. So basically the architecture that they have designed is a combination of SIMD pipeline, like the vector processor, as well as SISD pipeline, the pipeline that we have discussed so far, like the scalar pipeline. So Cray is one of the prime example of that I'm going to show some slide about that Cray. You might actually see Cray X1 or XMP, I guess, in CAB building, right? In the E floor, I guess. Have you seen that? Yeah, I will show you a picture of that soon. Then after this lecture, maybe you can go and see. So yeah, this is also the paper from Amdahl that you want to see. If you want to learn more about this topic, this is a lecture that we cover in Advanced Computer Architecture. It's the master course that we talk about this Amdahl law and why we need to use heterogeneity for better performance. So yeah, you can also optionally check these lectures if you're interested. Another limitations of vector processor is that they rely on memory bandwidth a lot. So even though your instruction is one, for example, so you have single instruction, but you want to do this single instruction on multiple data elements. So essentially you need to load a lot of data. You need to feed a lot of data to your pipeline, basically, right? And that means that you're gonna exhaust your memory bandwidth and basically the memory subsystem. So, and that's one of the reasons that we're gonna also, cover a lot about memory starting from tomorrow lecture. But essentially, memory is the bottleneck of many, modern processors. Okay, so any question? If not, I think we can let's check. Yeah, we can take 10 minutes break until 3:10, and then we will continue with this part of lecture. Okay, let's get back to the lecture. Now we are gonna see a little bit more detail about how we can design vector processors. And then we're gonna jump into GPU. Shall we get it started? Okay. So we already discussed about vector register. So each vector data register holds n m-bit values. So n is the number of basically vector elements. And each element can be m-bit, like 8-bit, 16-bit, 32, depending on your design. And we also have some control registers for vector processor. You already know about VLN, which is we specify the length of the vector operation, and also the stride, the vector stride operation value. We also have this VMask, which is essentially, we use that in order to mask some of the lanes of your vector. So for example, you have an array of 32 elements, and the operation that you want to do is just, you want to do it only on the first 16 elements. You don't want to do it on the basically the rest of your array. So you need to, basically you make this vector mask register that essentially you show in that mask register that you only want to operate on the first 16 elements. So that's actually one of the hardest things that programmers usually need to deal when programmers work with SIMD processor. And that's also one of the reasons that people don't basically it was quite hard to program a SIMD processor, and then we had to go to GPU to make it much easier for programming. So the maximum VLN can be n, which is the maximum number of elements stored in a vector register. And I already also talked about the vector mask register that you essentially, so you create this vector mask by some condition, and then that can mask your operation. So you can eliminate some of your vector elements on some specific operations. So this is also this vector functional unit. It can be, as I said, the functional unit can be pipeline. So here we have, for example, 6-stage multiply pipeline. This is an example of real machine that they use basically a vector processor, I mean SIMD, which is Cray-1. And in Cray-1, actually, you can see here that they have some vector registers, vector pipeline, as well as some scalar register and a scalar pipeline. So essentially, if back then, also in 1978, people realized that we cannot fully rely on data level parallelism. It's also important because we have sequential pipeline and sequential bottleneck, and it's important that we also accelerate that part as well. So this is the paper from Cray-1. If you're interested, you can read. I mean, the terminology is a bit old because the paper has been written in 1978, but it's quite interesting. And this is the picture that I was promised you, Cray XMP, that actually we have it in CAB eFloor. So next time you can be more careful and see it. Maybe you have already sit on this couch maybe and discuss. Yeah, but this was one of the supercomputer the past. This is the overview block diagram of Cray XMP. I'm not going to cover it at all, so you can check it if you want, if you're interested. And and some design detail. These are just some optional material for you if you want, if you're interested. Okay, and this is Seymour Cray, basically leader in supercomputer design. And he made this actually nice analogy that if you were cloning a field, which would you rather use 2 strong oxen or thousands of chickens? So that's exactly what they really mean here. So sometimes we use some powerful cores, like the few of or several powerful cores, like essentially many of these Intel processor, like the Xeon processor that we use in servers. So they have is multi-core, so we have several cores, and each core is quite strong and powerful. But in comparison, we also have GPUs that they have thousands of small cores. And those small cores are not capable of doing a lot of things. But depending on your application, if you're capable of distributing your load across thousands of chickens, you may actually benefit a lot from that architecture. Okay, and in this explanation of Cray-1, you can see that we have 16 memory banks. I'm going to cover a little bit more about this, but this is essentially because we need high memory bandwidths. So as I discussed in SIMD architecture, one of the limitations is that we rely on memory bandwidth a lot, and we need quite a lot of bandwidths. So yeah, that's exactly what I'm going to cover now. So basically, we need to require to load and store multiple elements, and elements are separated from each other by a constant distance that we already discussed. We call it the stride. So assume that our stride is 1. So elements can be loaded in consecutive cycles if we can start the load of 1 element per cycle. So that's the key. So if you can start the load of 1 element per cycle, you can get to this beautiful pipeline that you have your elements loaded per cycle. But this needs a lot of throughput and a good design that we're going to see. So essentially, you're going to sustain a throughput of 1 element per cycle. That's the goal. So how we can achieve that is essentially with multi-banking. So we need to bank the memory. So and also interleave the elements across banks. So we're going to see here. So this memory banking that we also see in Cray-1, that they have like 16 banks. So here your memory is banked by 16 banks, and for each bank you have memory data register and memory address register. So essentially you can access these banks concurrently. And yeah, so basically, as long as you don't have bank conflict, which means that you have consecutive accesses to the same bank, and you have basically, you have enough number of banks. So we're going to see that also soon. You're going to sustain that throughput. So here is like our example, like this vector register and our memory banks that we have 16 memory banks. So the address that we're going to load is like the previous address plus stride. So if a stride is 1 and basically consecutive elements interleave across banks, meaning that the first element is in this bank 0, the first element 1 is the bank 1, element 2 in bank 2, element 15 is in bank F, and then again, element 16 is in bank 0. So if we actually interleave our elements nicely through these banks, and as I said, the number of banks is larger than bank latency, then we can actually sustain that 1 element per cycle throughput. This last item is also quite important. So imagine that your bank latency is 11, for example. It takes like 11 cycles to load from your memory. So you need at least 11 number of banks. And usually in computer architecture, we really like to use power of 2 numbers. So that's why, for example, in Cray, we had like 16 banks. So let's see some example such that we can learn more about these topics. So this is the basically the operation, like the scalar code that you want to run it. So you have this 4 iterated from 0 to 49, and essentially you want to do, add element-wise 2 vectors and divide it by 2 and store it to vector C. So you can actually write a scalar code for this code. It can be using MIPS ISA. It can be any random ISA as well, like here, for example, that you move basically some value like 50 because you have the number of iterations that you have is 50. And then you basically move the address of vector A to register 1, then the address of vector B to register 2, and so on and so forth. And then you basically need to load element. You do addition. You do division by 2, which you do shift right by 1. And then you store it. And then you need to basically jump back to this label X. to have this loop. So this is a simple assembly code that can run this basically code that we have. Assume that we have these number latencies. For example, for this move, the latency is 1. These instructions, all of them, they have 1. For load instruction, we have 11 cycles latency. For addition, we have 4 cycles. For shift, we have 1. For store, again, we have 11. And for jump instruction, we have 2 cycles latency. So these are our assumptions. Okay. So here you have 304 dynamic instructions. So you have 4 instructions here, and then you have a loop here. Then essentially you need to count the number of iterations that you basically loop here. So you have 1, 2, 3, 4, 5, 6 instructions, and it's gonna iterate 50. So it's gonna be 300 instructions, dynamic instructions that you're gonna run here, and 4 instructions here. So overall, you have 304 dynamic instructions. So let's make some calculations. So for a scalar code execution time, the execution time on an in-order processor with only one bank. So the first 2 loads cannot be pipelined. So you need to have basically 2 11 plus 11 cycles for that. And then essentially what you have 11 plus 11 plus 4 plus 1 plus 11 plus 2 times 50 and plus 4. So this is basically essentially 2004 cycles for a scalar execution. Of course, with some simplification in analysis. So yeah, the scalar execution time and in-order processor with one bank with 2 memory ports can be basically be faster because you can actually pipeline the first 2 loads. So the first 2 loads can be pipelined. Then essentially your latency of the total of these 2 loads is gonna be, so you need to spend like 11 cycles for the first load. But after that, the second one will, because it will also start 1 cycle after this one, after the first one. So overall, this 2 load will be done by 12 cycles. And that's why we have now 12 cycles for the load, and our execution time is now around 1,500 cycles. Now let's see how we can actually improve it with vector processor. So a loop is vectorizable if each iteration is independent of any other. So in this example is actually the case. So every iteration is independent of the next iterations and other. So it's vectorizable easily. So basically what we can do here is that we move 50 to our vector lengths, assuming that our vector processor can sustain 15 elements, or your vector registers are, they can store 50 elements. So your vector length is 50, and your stride we consider as 1 because, I mean, these 2 vectors, we assume that they are consecutive in the main memory. And then basically we have these vector load instructions that you load array A to vector register 0, and then vector B to vector register 1. And then you do this vector addition, and then you do vector shift by 1, which is division by 2, and then you store it. So the whole code that you had before with a lot of loops or so, now is just some vector instructions. And if you count the number of dynamic instructions, we have only 7 dynamic instructions. And that immediately should show why these architectures are quite energy efficient, because so you really amortize the overhead of fetching and decoding instructions on multiple data elements. So the latency for these operations. For vector length, basically these move instructions, we again consider only 1 latency, 1 cycle. So for vector load, since we have a pipeline vector processor, right? So vector process pipeline, essentially. So you need to spend 11 cycles to have the first element of your vector in your vector register. But after that, every cycle, assuming that you have enough number of banks, you're going to have your basically elements. So in the end, the latency is going to be 11 plus VLN minus 1. Is it clear? And for the second load, again, the same thing. We have 11 plus VLN minus 1. For addition, so again, the first element takes 4 cycles. But then we have, since we have a nice pipeline, is VLN minus 1 and so on and so forth. So this is the latency numbers for these instructions. So assume that we have no chaining, like there is no vector data forwarding. We're going to see a bit about it soon. So basically, output of a vector functional unit cannot be used as the direct input of another. So this is one big optimization in vector processor design, that you basically chain all these functional units, such that the output of one goes to the input of one. So you can use this, produce consume manner. So the one functional unit produce a data element that you're going to consume it immediately in another functional unit. But for now, assume that we don't have that kind of architectures, and the entire vector register needs to be ready before any elements of it can be used as part of another operation. So these are the assumptions that we have. And we have only 1 memory port for now, and 16 memory banks, such that we can nicely interleave everything. So this is going to be basically the time line of this run. So you're going to spend like 2 1 cycles first, and then 11 VLN minus 1, which is 49, then 11 VLN minus 1, and so on and so forth. So you're going to end up having 285 cycles, which is quite a lot good performance improvement. So we already discussed about why 16 max, because we have 11 cycle memory access latency. So it ensures that we can have, 1 element per cycle. So yeah, so if a stride is bigger than 1, then you may end up, having some conflicts, and that's actually a big topic about how we can, reduce, bank conflicts, which I don't have really time to go into detail of them. Okay, so yeah, so this vector chaining that I already mentioned, like you load, and then the output, the data that you have is going to be fed to the next instruction immediately. So with this, you chain your functional units. So if you have that, your timeline is going to be a bit more complex, and you're going to also see some performance improvement. So essentially what's happening is that, so for the first load, you have 11 and then 49. For the second load, you spend 11, but as soon as this moment, you already have the 2 elements, the 2 first elements. So you can actually start the addition for that part of your operation. So you can see that you can hide some of these latencies. And after 4th cycle, then you have actually the output for addition for the first 2 elements. Then you can actually start the shift for that element. And then as soon as you have basically your results, you can start a store. But for a store, you actually need to wait until this load is also end, because we are limited by the number of memory ports. So we consider here that we have 1 memory data port that can be used for reading, loading from memory and storing to the memory. So essentially, you cannot pipeline more. So here you need to wait. Yeah. So with that, you end up having 182 cycles. I already mentioned that. If you imagine that we have 2 load ports and also 1 store port in each bank, so we have a nice luxury here, then actually you can have this timeline, which you can actually issue these loads together, like in pipeline. And this is the first load, and then just 1 cycle after that, you can start the second load, and so on and so forth. So with this architecture, you're going to end up having 79 cycles, which is like around 19 times performance improvement. But we add also a lot of hardware complexity for this example. Any question? Okay. So now what we can do, if we have some conditional operations in a loop, So, and that's the idea of using mask operation that I already mentioned, like using VMask. So, yeah, imagine that you want to implement this loop code that for every iteration, you check the value of AI, and if it's not 0, then you do some operation. So essentially what you need to do is generating this VMask. So here we say that VMask will equals to V0. V0 is A, the vector A. That V0 should not be, basically should not be 0. So for those elements that the data is not 0, then you set the corresponding bit in your VMask register. And then after VMask, once you're done with VMask, you can actually continue operation. And then your operation is going to be masked for those elements that vector A is 0. So this is, I mean, quite simple for this application, but sometimes it's quite sophisticated and very hard to implement. Okay, this is also called as predicated execution. That's yeah, so that you predicate some of the execution. So basically, you have the same pipeline for all, whenever you have a branch. So in normal architecture, like the MIPS architecture that you have learned, so whenever you have a branch, you have like taken or not taken, and depending on if you take the branch or not take the branch, you may run some different instructions. But when you use this predication, what it means is that essentially you go through the same pipeline, you go through the same functional unit, but if you predicate that corresponding bit or corresponding element, you don't do that operation. So it's going to be like no op for that corresponding element. So this phenomenon is actually called as predicated instruction, which is actually also quite useful for GPUs. Okay, so yeah, this is also another example with masking that you can also check it if you're interested later. But essentially, this example shows that sometimes creating that mask register is not really easy. And yeah, and we have different ways of implementing that. We can have simple implementation that we execute essentially all N operations, and we just turn off results right back according to the mask. So we do the operation for every element, but we don't write back the result for those elements that we have masked them, basically. But it can be also more intelligent that we do density time implementation, that we scan mask vector and only execute elements with non-zero mask. So it adds some complexity. Which one is better? It really depends on how many elements are you masking. If you are masking many elements in your vector, probably you're gonna use this implementation because this is so, more efficient. But if you're gonna use most of your elements and you're gonna just mask a few of them, then probably this architecture is gonna be better because it's much simpler and it has low cost. I already discussed trade-off. Any question? Okay. So yeah, some issues about, as I said, the stride and bank count, that it should be basically a stride and bank count should be relatively prime to each other, and there should be enough number of banks such that we can sustain this 1 element per cycle throughput. It's actually nice food for thought that why they should be relatively prime, so you can think about it at home. But essentially what happens is that when we want to run this matrix multiplication, as I said, we have different strides. So we already discussed this example that when we are loading matrix A, we have a stride of 1. When we are loading matrix B, we have a stride of 10. And that causes changing different strides, and that can lead to bank conflicts. And bank conflicts mean that you have 2 consecutive or more than 2 access to the same bank. So these accesses are going to be serialized. They cannot be addressed in parallel, and that is killer for such architectures. So there are many ideas to how to minimize bank conflicts, better implementation, using more banks, more ports, and also better mapping of address to bank, which is like using some randomized mapping, which is not really, so the way that we map our data to the memory is not that simple, that we basically every address, you can calculate the position easily in the main memory. So essentially we have some randomized mapping such that we can reduce bank conflicts. I'm not going to cover it. If you are interested, you can actually read this beautiful paper from ISCA in 1991, pseudo-randomly interleaved memory. And this is the paper. Question? Okay. So array versus vector processor, so the distinction is so purist. And in the end, the most modern SIMD processor, as I said during the lecture, are a combination of both. And they exploit data parallelism in both time and space. And GPUs are a prime example that we will cover now in more detail. Let's see how much time we have, but let's see. Okay. So GPUs, graphics processing units, are SIMD engines underneath. So the instruction pipeline operates like a SIMD pipeline, e.g. as an array processor. However, the programming is done using threads, not SIMD instructions. And that makes a lot of difference. So to understand this, we need to basically go back to our parallelizable code example. But before that, I like to distinguish between program model and also execution model. So the program model is at the software level, and that refers to how the program expresses the code. It can be sequential code using von Neumann. It can be data parallel using SIMD, because actually modern architecture, they also allow you to write SIMD codes. So it can be, you can use SIMD instructions. It can be data flow machine that you use data flow ISA. It can be multi-threaded, whatever. So that's the program model that the programmer expresses the code. But we also have execution model that can refer to, execution model refers to how the hardware executes the code underneath. And that can be quite different from the program model. Like out of order execution, even though sequential von Neumann, still in most of the architecture, we are using sequential von Neumann basically code, but we run them on out of order processors. And that's, we have seen last week that out of order execution is, internally you are actually using kind of data flow paradigm to run your application. And vector processor, array processor, data flow processor, multiprocessor, multi-threaded, essentially the way that you implement your hardware, your CPU. So execution model can be very different from the program model, like as we discussed, von Neumann model implemented by an out of order processor. Or this single program multiple data that we're gonna see soon, which is implemented by a SIMD processor that we call it GPU. So let's take a look at this parallelizable code. So we have this 4 operation on these 2 array. So essentially you have different iterations and all of them are separate. So we want to examine 3 programming options to exploit instruction level parallelism. So you have huge amount of instruction level parallelism here, right? Because every iteration is independent. So we'd like to use sequential, like in SISD architecture, like the MIPS ISA, for example. We'd like to also use a data parallel, SIMD, which have been seen so far, and multi-threaded that we're gonna see. So in SISD architecture, it can be executed on a pipeline processor, it can be executed on out of order, because independent instructions executed when ready, and different iterations are present in the instruction window and can execute in parallel in multiple functional units. So, and it can be also super scalar or VLIW processor that we haven't covered in detail in this semester. So that shows some difference between program model and execution model. In SIMD architecture, so if you use it for a SIMD programming, so you need to actually allocate every iteration to a vector element. So the programmer or compiler needs to generate a SIMD instruction to execute the same instruction from all iterations across different data elements. So we have this vector instruction of load, then another load, and then addition, and then a store. So you've seen it so far. And basically, it's best executed by a SIMD processor like the vector or array. We can also do it in a multi-threaded. So we can realize that here that each iteration is independent. So we can actually allocate each iteration to one thread. So you're going to have, so the program compiler generates a thread to execute each iteration. And each thread does the same thing, but on different data. So essentially, every thread will run this code like the load, add, and store. But they are operating on different data elements that we call it actually. So it can be like SIMD machine, but it's also called a single program multiple data because you have multiple threads, and essentially each thread is going to run the whole program. And we call this paradigm as single program multiple data, that you have single program, which is sequence of instructions that's going to run or executed on multiple data elements. So we call this paradigm SPMD. And but this SPMD is a program model, and it can be executed on a SIMD machine, which is GPU. So GPU, in short, they are using SPMD programming model, but they are using a SIMD machine underneath to accelerate. NVIDIA call it actually as SIMT. So they call this machine SIMT, like single instruction, multiple thread. So when you talk about SIMT, you really basically combine these two paradigms. So you mean that the programming model is SPMD, single program, multiple data, and underneath you are using SIMD. So a GPU is a SIMD or SIMT machine, except it's not programmed using SIMD instructions. It is programmed using threads or SPMD program model. And each thread executes the same code, but operates at different pieces of data. So the good thing is that each thread has its own context and can be treated, restarted, executed independently. So each thread has its own context, meaning that has its own registers. So that's why actually GPU needs a lot of registers. So like, for example, in MIPS, I think the version that you have learned in this course, per core, we have 32-bit registers, as far as I remember. But for example, in NVIDIA architecture, every core, so we have hundreds of those cores, but every core in GPU, it has like 64K 32-bit registers. So it's huge. And that's the main reason is that you need to keep the context of all threads on chip, such that you can switch fast between them in order to hide latencies. So a set of threads that they execute the same instructions are dynamically grouped into a warp, which is the NVIDIA's terminology, or wavefront, which is AMD's terminology, by the hardware. So essentially, it's not the programmer basically task to group instructions in SIMD manner. Basically, it's happening dynamically in the hardware. So the programmer just writes the code for one thread, kind of, is a scalar execution. But dynamically, when your application is running on the system, the hardware actually dynamically group instructions that they are basically, the threads that they are running the same instructions into a structure called warp. So this is the beauty of a GPU, that programming does not really need to deal with vector lengths and those stuff. So it's everything handled by the hardware. And a warp is essentially a SIMD operation formed by hardware, which is nice. So let's back to our example. So when we have SPMD on SIMT machine, we have warp, which is a set of threads that execute the same instruction. So it can warp 0 at PC program counter X that do load, and then warp 0 goes to program counter X plus 1 that do the second load, and then addition, and then a store. And you can have several of these warps, and we're going to see also later. Any question? Okay. So yeah, so GPUs, they are SIMD machine underneath, but SIMD is not exposed to programmer. And that's the reason that it makes them so, I would say, powerful, because the program model is so easy, relatively, and people, have used it a lot. So SIMD, so let's make some comparison between SIMD and SIMT execution model. So in SIMD, you have a single sequential instruction stream of SIMD instruction. So each instruction specifies multiple data inputs, and you need to deal with vector load, vector addition, vector store, and vector lengths. For SIMT, you have multiple instruction streams of a scalar instruction, and that makes the difference here. So threads group dynamically into warps. So you really need to deal with only simple load or addition or a store. So the programmer, when you program, you don't need to think about, I'm doing this operation on vector. You really need to think about, I'm doing this operation on a single element, like the way that you write code for normal CPUs, basically. So that, and the only thing the programmer needs to specify is the number of threads that we need to run. So there are two major SIMT advantages, is that we can treat each thread separately. So basically, you can execute each thread independently on any type of scalar pipeline, like MIMD processing, and can group threads into warps flexibly, which means that we can group threads that are supposed to truly execute the same instruction, dynamically obtain and maximize benefits of SIMD processing. So you are not that rigid about your vector instructions. Whenever you have, even though the implementation of that is a bit actually hard in off-the-shelf GPU, let's say, but there are many research in that line that. So whenever you have some warps, that you may have some mask thread, some warps that, essentially because you are doing SIMD kind of instruction, at some point you're masking some of the threads. But those warps, you're going to see that some threads are running the same instruction. So they are in the same program counter. So you can essentially combine them and make a full, efficient warp. You're going to hopefully see with one figure soon, but if we couldn't, we're going to, I guess, have it tomorrow, very early in the beginning of the lecture. Okay, so so fine-grained, basically, essentially, what we have in SIMT is that you have several warps, and you have fine-grained multi-threading of warps. So you are switching between warps in a fine-grained manner. So assume a warp consists of 32 threads, which is not a bad assumption. Actually, most of nowadays GPUs, NVIDIA GPUs, they are using 32 threads. And if you have 32,000 iterations and one iteration per thread, eventually you're going to have basically 1,000 warps in your system. So now you have 1,000 warps, and these warps need to be scheduled to your pipeline. So they are interleaved on the same pipeline, which we call it as a fine-grained multi-threading of warps. So you need to switch the pipeline between different warps concurrently. So which means that warp 0, for example, executes at program counter X. Warp 1 then also works on program counter X. At some point, you're going to see warp 20, for example, is at program counter X plus 2. So you have different warps, and they can be on the different actually program counters. But essentially, they're gonna be executed concurrently on the same functional unit. So that's why we need to interleave them on the same pipeline. Okay, so we haven't also covered fine-grained multi-threading, but this is a very basic idea of that. This is the normal architecture that I think you have seen so far in prior lectures. So you have this, pipeline MIPS kind of processor. So essentially, when we want to run it in a fine-grained multi-threading, the basic idea is that you need to increase the number of program counters. So for every thread, you need a separate program counters because you want to fetch instructions from different threads. And you need to also add enough registers. So essentially, you're going to have register file or registers per thread. That's the important part. In parallel programming, when you program multi-threaded, whenever you want to switch from one thread to another thread, you end up having a lot of cost of context switching. What that means is that you need to store the context of that thread. I mean, you don't do that because it's handled automatically through the operating system. But what's happening is that the context of that thread needs to be stored in the main memory, and the context of another thread that you want to execute needs to be loaded from the main memory, and that causes a lot of latency. Which call it context switching. So you need to switch the context. But in the paradigm of fine-grained multi-threading and also GPUs, because you want to quickly switch between warps, you need to keep the context on chip, such that it's just switching, changing some control registers or multiplexers. That I was running warp 0, now I just want to run warp 1. And the registers of warp 1 is ready. I just need to load them from the register file. And essentially, you don't really need to do context switching. And that's the beauty of GPUs and how they provide a lot of good performance, but at the cost of like 256 kilobyte register file per GPU core. Okay, so if you want to learn more about fine-grained multi-threading, I would encourage you that you watch this lecture from past. It's a beautiful lecture and it's quite insightful. Okay, so warps and warp level fine-grained multi-threading. So warp, essentially, as I said, is a set of threads that execute the same instruction on different data elements, or this SIMT, which is NVIDIA terminology. Or threads run the same code. And yeah, basically warp the threads that run lengthwise in a woven fabric. So that's the reason that they call it warp. And this is our thread warp, that each warp has a common PC. And per warp, we have a scalar thread, basically a scalar thread, W, X, Y, and so on and so forth. And you can have several of these thread warps that you need to basically, schedule them nicely. So your pipeline, if you think about it, you have a front end in your pipeline and you have a back end in your pipeline. So in the front end, you're actually operating on warps, which means that you load instructions per warp. You don't really load instructions per thread. So everything is happening based on warps. So you schedule warps, you decode warp level instructions. So when you want to store instructions, you store instruction for a warp. But in the back end of your pipeline, which is you have your ALUs and register file, those stuff. So you need to operate per thread, basically, essentially. So that's the meaning of this essentially figure here. So this is a high-level view of a GPU. We have several cores in NVIDIA terminology. In the past, I think still they may also use this terminology because it's coming from graphics. That they call this core as shader core. If you don't know graphics, you cannot really understand what it's called shader. But essentially, this course has been used for graphics to do shading. And that's the reason that they call it shader core. There were actually some intelligent people in the past that they realized that if they make a nice analogy between the pixels and data, they can actually use shader cores to run normal applications. So whenever they have some, let's say matrix multiplication, they just made this analogy that, okay, I consider every element of my matrix as some pixel, right? Pixel on your picture. And then they really use a graphics library to do operation on those pixels. And after all, when they have the output, they just need to translate back pixels to the output that they were looking for. So they actually showed they showed the line to NVIDIA that, okay, you have such things, so why not, providing the programming model such that people can use it? And essentially what NVIDIA provided is just improving the architecture to make it a little bit more general purpose. So now we are in the, paradigm of GPU, general purpose graphics processing units. And as well as a programming model that you may heard of, like the CUDA programming, that makes life easy. You can easily use a GPU to run your parallel applications. But yeah, so if you're interested, you can actually check those papers that the people use GPU to run parallel application in 2002 or so. And those are really amazing. Okay, so yeah, let me check. I think we still have some 4 minutes. So I think I will be done with the main part of this lecture actually in 4 minutes. So yeah, so we have latency hiding with warp level fine-grained multi-threading as we discussed. So whenever you have a warp, that is, for example, your warp ends up having loading and data. So you have a long latency for that load instructions, and your warp is gonna be stalled. So then what we can do easily here is that switch to another warp. So by switching among the warps, you end up hiding latencies. It's kind of different from instruction level parallelism that we have seen in out-of-order execution. In out-of-order execution, you've been relying on switching between independent instructions of the same thread such that you can hide latencies. Yes?
Can you maybe quickly explain again what actually really happens when there is a warp? So what is really done? Because you introduced this concept really quickly.
Yeah. So yeah, I think I have a slide about the program model of GPU, but what's happening is that as a programmer, you mentioned that I want to do addition. Basically, for example, you write a code that the function that you want to run on GPU is just simple addition, for example, and then essentially you want to do that addition on a vector of, let's say, 1,000 elements, but you consider these 1,000 elements, for every element you consider one thread, right? So basically the programmer specifies the total number of threads, and then basically the GPU is gonna, the code is gonna be invoked for GPU. So your kernel is gonna be run, executing GPU, and you have thousands of threads. And in the hardware, so in the hardware of GPU that you have multiple cores, so every core is gonna take some amount of these threads. For example, if you have 1,000 threads and you have 10 cores, every core is gonna run like 100 threads, basically. And then essentially these 100 threads is gonna be grouped into warps when they are running. And that warp is not really exposed to the programmer. So
all the thread warps actually, like all the threads that are grouped into running on one process.
Yes, threads that they are on the. Yeah, exactly. So warps are in the, yes, one core, but it can be also several warps in one core. But yeah, but the important thing is that threads that they are in the same warp, they are operating on the same instructions in a kind of interlock manner. So lock step manner. So basically you do your operation and you need to wait until go to the next instruction. So all threads should be done by that instruction. Okay, so tomorrow we're gonna continue from the part that we basically left off, and after that we're gonna basically start the memory organization. See you tomorrow. Thank you.